Hello, today we're going to be talking about a few different things here, all about vectors. We're going to be looking at algebraic addition of vectors, then we'll talk about component vectors, and then lastly we'll talk about finding the magnitude of vectors. So for starters, let's say that we have two vectors that are applied here, and we want to see really what the vector is from my first initial point to my last terminal point. What this guy would be right there. So we don't have to deal with two separate vectors. We want to combine them. Using the head to tail method, we know that we can combine these geometrically if we graph them out, and then we've got this. But you know what? That is a little bit more time consuming than we would ideally like. We like something a little bit more direct. We can do that. I've got the components here for my two vectors. I've got this 4, 3. I've got this 2, 0. In order to add these together, so let's say that this is, let's call it vector C. Why not? Okay, and this is vector D. I can just take C plus D, and that would give me my new vector, which I can call E. And that is simply a matter of substituting at this point. I've got 4, 3 plus 2, 0 would give me E. Now, what I like to do is just take this 4, 3 and the 2, 0. I know I'm adding them. My horizontal is only going to affect my horizontal, and my vertical is only going to affect my vertical. So I stack these up, and I think it's a lot easier to see if you just do something like this. If this helps, add straight down. Your horizontal with your horizontal. 4 plus 2 gives you 6. 3 plus 0 gives you 3. So the components together here of E, these added together give you E. So E would equal 6, 3. I just put the horizontal with the horizontal and the vertical with the vertical. That is it. That is a simple way to add two separate vectors together. We can do the same thing. Here's a sample. We've got 0, -5, and -3, -3. Okay, I want to find this guy right here. So how could I do that? What do you think? I can add them up. You can stack them like this. 0 and -3 give you, and -5 and -3 give you. There you are. That's it. So we like being able to work with the x, then the horizontal, and the y, the vertical, separately with vectors. It makes the addition very easy. What we often do is we work with them in ways that are called component vectors. So this format we can see, but we also see this, and this makes it a lot easier when we're doing, and here we like to kind of stack these guys like this, but you may not just be adding one or two vectors, you could be adding several. And when we're working with vectors in different ways and working with like algebraic equations for vectors, it is a lot easier to put them in this style. So all this means is that when I've got an I, so it's just your horizontal component. When I've got a J, that is your vertical component. This is the same thing as saying in the pointed brackets 6, comma 3. We just designate I whenever something is times I. That just is just your indicator of, hey, this is my horizontal movement. When it's it's got the j attached to it. That's hey. That's my vertical movement. Okay? So if I want to rewrite -7, comma 2 here in the pointed brackets as component vectors with I and j, what would I do? I've got -7 for my horizontal. That becomes -7 I and 2j. That's it. So be familiar with both forms. You will see both. Lastly, magnitude of a vector. And when we think about these vectors, it helps to draw pictures as we've done so far and have some sort of visual to connect it to. So I'm going to draw this vector W. First of all, let me put the component vectors in there. So I've got 3i that tells me that I'm going 3 positive, and then I've got the -4j. So that's my vertical, and I'm going down because that's negative. We're following the good old same rules that we've been working with for positive and negative in graphs for a long time. So this is the vector that I've got right there. Since this is the 3i is horizontal, since the 4j is vertical, the angle that I've got right here where the two meet is a right angle. So hey, I have got a right triangle here, and I happen to know two sides. Is it possible to get this third side, which in this case happens to be the hypotenuse? Of course it is. When you're looking for magnitude, take your two component vectors and you square them. And you add them and you take the square root, and that becomes your magnitude. Okay, the magnitude is the measure of how much for that vector. So in this case, it is the square root of, well, whatever. I'm just going to plug in a for just whatever is your horizontal component. Oh, I should have put a b right there. Okay, those squared. And actually, we can even forget about the I and the j at this point because we don't really care about the direction. The I and the j connect to the direction. We're looking at magnitude. Magnitude is separate from direction. So if, let me rewrite this a little bit then. If W in this case is equal to AI plus, okay, it's the square root of a squared plus b squared. It's the Pythagorean theorem, which we have seen for years, and it will, I mean, it makes sense. This is a right triangle. This is the hypotenuse. That would be the side that would complete it. And so we can solve for the magnitude of W, which is denoted by like these double absolute value bars here. So square root of a squared, I can just make a be 3, so 3 squared plus 4 squared. Same thing as 9 plus 16 equals the square root of 25, which equals 5. So the magnitude of W is equal to 5. That's that missing hypotenuse there. It worked out very nicely. We didn't have any square roots or anything, but we could. We could. That's fair game. That's fair game. Same process works. So what I would like to do is let you work on one of these on your own. If I have a vector here, A, that has components -5i, that's your horizontal, 12j, that's your vertical, what would the magnitude be? And work on that, bring that to class, and we will discuss. Also bring your questions too, of course. All right. Thank you for your time, and I hope you have a great day.